Hey there guys, how's it going? Mike coming back at you with another video on precalculus. In the previous video, we talked more about roots of polynomials. We talked about how to narrow down the possibilities in terms of how many we can have, how many negative, how many positive, what rational roots could we have, and then some other useful handy facts about zeros of polynomials. In this video, we're going to change gears a little bit, and we're going to talk about rational functions and properties of graphs of rational functions. So first of all, what are rational functions? A rational function, for our purposes thus far, is just going to be a quotient of polynomials, something of the form p of x over q of x, where p and q are polynomials on their own. In general, a rational function simply means a quotient of two functions. In the next chapter, we're going to get to exponential and logarithmic functions as well. So a rational function could be, say, a logarithmic over a polynomial or a polynomial over an exponential. But so far, and really for our purposes in this course, we're really just going to be focusing on rational functions as quotients of polynomials. The domain of a rational function is all real numbers except those which make the bottom equal to 0. We can't have an x value that makes the bottom 0 because then we're taking some number on top and we are dividing by 0 and that breaks the internet and we just can't have that happening. So find the domain of these two functions here, 3x minus 7 divided by x squared plus 8x plus 12. And then after that, 4 divided by x squared minus 6x plus 9. So we'll work with the first one here. We are going to take that bottom and set it equal to 0 and solve for x. So to do that, we need to factor it. And x squared plus 8x plus 12 luckily nicely breaks down into the factors x plus 6 and x plus 2. If the product of these two factors is going to equal 0, then either one of these guys has to be 0 on their own. So that means that either x plus 6 is 0, which means x is negative 6, or x plus 2 is equal to 0, and that means x is equal to negative 2. So these are the two values that we cannot have. We throw these guys out. Therefore, the domain of f of x here is all real numbers except these two guys. So if you put a diagonal line through that, those are the only two x values that we cannot have. Everything else is good. The second one, x squared minus 6x plus 9. We're going to set that equal to 0 and solve for x. But that is a perfect square. That is x minus 3 quantity squared. So that means the factor x minus 3 has to equal 0, and that means x is equal to 3. So again, that's the x value that we cannot have in our domain. Every other x value is fine. Before we talk about important features of graphs of rational functions, just some terminology that I want to introduce here that we'll be using in some definitions later on in this video. So if you see x and then a right arrow and then an a with a plus in the upper right hand corner, what we're saying is that x approaches a from the right. So you're starting somewhere to the right of your x value. If I draw a very short real number line here, here's my specific x value a. If I start somewhere to the right of a, and then I move to the left towards that a value, that's what we mean by x approaches a from the right. We're looking at x values that are greater than a, and we're moving towards a. Very similar to that, but instead of a plus in the upper right-hand corner, it's a minus sign in the upper right-hand corner. That means x approaches a from the left. So there's my x value a. Now I'm starting somewhere to the left of a, or I'm starting with x values less than a, and now I'm going to move right to get to a. So that's what we mean by x approaches a from the left-hand side. We're starting to the left of a, and then we're moving right. Then we have x approaches positive infinity, or we also say x increases without bound. So we're just letting x get larger and larger and larger, and it's going to keep going all the way to the right. It's never going to stop. And then lastly, we have x approaches negative infinity, or x decreases without bound. That's to say we're moving all the way left on that real number line, and we're not going to stop. It just keeps going left and left and left. So now the features of graphs of rational functions. The important features that I want to talk about here are asymptotes. There are two main kinds. There is a third kind which I will touch on at the end of this video. Overall, not as heavily focused on, but these first two are definitely asked about more frequently. Those are vertical asymptotes and horizontal asymptotes as well. So first up, vertical asymptotes. The line x equals a is a vertical asymptote on the graph of a rational function f of x if the function increases or decreases without bound as x approaches a from the left or from the right. So again, the function increases or decreases without bound. The function goes to negative infinity or goes to positive infinity as x approaches a from the left or from the right-hand side. The function does not have to do the same thing. It does not have to increase without bound from the left and from the right. As long as your function is doing one of increasing or decreasing without bound as x approaches from the left or from the right, and again, it only has to be one of those. It doesn't have to be increasing from the left and also doing something else from the right. As long as it's doing one of these from one of the ways, then that vertical line is a vertical asymptote. And with these graphs here, you see a couple samples here. In the graph on the left-hand side here, this vertical line here is x is equal to positive 1. We see that as we approach negative 1 from the left-hand side, the function in blue here is shooting down. It's shooting down very, very fast. As we approach 1 from the right, this function is skyrocketing up very, very quick. The function is never going to actually hit that dashed line, but it will get very, very, very close to it. So close to it that it may seem like it's going to hit that line. But this is one example of a vertical asymptote. From the left, the function is decreasing without bound. From the right, the function is increasing without bound. The graph on the right-hand side here, we have a vertical asymptote at x is equal to 0. In this case, the function is increasing without bound from the left and from the right-hand side. These are the two most common types of situations you would see in regards to having vertical asymptotes. Well, this is pretty easy to see just by looking at the graph, but if you're just given the function, how would you tell where you have a vertical asymptote? If you have your rational function, p of x over q of x, where P and Q have no common factors. That is a very, very important piece of this statement to keep in mind. So if P and Q have no common factors, and an x value, call it A, makes Q of x equal to 0, then x equals A is a vertical asymptote of your function, of your rational function f of x. So again, you have your rational function. There are no common factors between the top and the bottom. If an x value makes the bottom equal to 0, then those x values are your vertical asymptotes. Now, what do you do if P and Q do have common factors? Then for the purposes of finding vertical asymptotes, you cancel out all the common factors. Then you find the values of x that make Q equal to 0. Those x values are going to be your vertical asymptotes. So let's do a couple samples here to see how we would do this. So first we're going to find all vertical asymptotes of f of x right here. X squared plus 5x divided by x squared minus 9x plus 20. Now when you see a problem like this, first thing you always want to do is factor out the top and factor out the bottom. And you want to check to see then, are there common factors? So here I factored f of x. The top breaks down into the factors x and x plus 5. The bottom breaks down into the factors x minus 4 and x minus 5. Clearly, there are no common factors here that we would have to cancel out. So the top and the bottom have no common factors. Now we just find the values of x that will make the bottom equal to 0. Well, x minus 4 times x minus 5 equals 0. That is pretty straightforward to find your x values. We see that that gives us x equals 4 and x equals 5. So those are going to be our two vertical asymptotes for f of x here. All right, now we'll go on to finding the vertical asymptotes for g of x here. So again, we're going to start by factoring g of x. The top breaks down into the factors x times x minus 7. The bottom breaks down into the factors x times x minus 2 times x plus 2. We see that there is a common factor between the top and the bottom. They both contain that factor of x. So for the purposes of finding vertical asymptotes, and I specify for the purposes of only finding vertical asymptotes, because when we talk about horizontal asymptotes, you'll see that we're going to need those things. But solely for finding vertical asymptotes, we cancel these guys out. There we go. And we're now left with x minus 7 over x minus 2 times x plus 2. Now the top and bottom have no common factors. Now we find the x values that make the bottom equal to 0. It's not too complicated to figure out setting the bottom equal to 0. It's not too hard to find out that your x values are -2 and +2. So those are going to be your vertical asymptotes. So that's how we find vertical asymptotes of a given rational function if you're not given the graph. The other type of asymptote I want to focus on heavily here are horizontal asymptotes. The horizontal line, y is equal to b, is a horizontal asymptote on the graph of a rational function f of x if the function approaches b as x increases or decreases without bound. So what we're looking at here, if I draw a quick little sketch here, my x and my y-axis. The dashed line at height b here is a horizontal asymptote if the function approaches this value. As x increases or decreases without bound. We see here that this function, I'll call it f of x here, it is approaching this dashed horizontal line. It's never actually going to hit that height, but it will get very, very, very close to it, and it flattens out there at that dashed line. Now, just like vertical asymptotes, where we said that it doesn't have to be doing something from both sides, it can only be doing it from one, same type of thing happens here. We could have it where our function is also doing, say, something similar to that. I'll make this the actual graph of a function here. A function could, say, be doing something like that. And this is still a horizontal asymptote because we have our function approaching this dashed horizontal line for some part of it, I should say. But trying to figure out horizontal asymptotes graphically is not really something that we do. We're more focused on how do we figure out horizontal asymptotes algebraically. So this one is perhaps familiar to some of us. This is sort of the three-case test to see what our horizontal asymptote is if we have one. So you have your rational function given to you. The numerator is a polynomial a sub n times x to the n plus 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 all the way down, like we've seen before, and the bottom is some other polynomial b sub m times x to the m plus 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 all the way down. So this is your rational function. Again, the leading coefficients on the terms with highest power in the top and bottom are not 0, and we're assuming that the degree of the numerator is n and the degree of the denominator is m. We have three cases here. And it's all based on, is n greater than m, less than m, or are they the same? First case, if n is greater than m, so if the highest power of x on top is greater than the highest power of x on the bottom, then there is no horizontal asymptote. Case 2, if n is less than m, or if the highest power of x on top is less than the highest power of x on the bottom, then the horizontal asymptote is going to be the x-axis. Third and final case, this case is where the highest powers of x on the top and bottom are equal. So if n is equal to m, then the horizontal asymptote is going to be the ratio of the leading coefficients. It's going to be a sub n divided by b sub m. We don't care about what all the other terms are doing in here. Everything over here, we don't care, and everything down here, we don't care about. It all comes down to what is happening with those leading terms there, the term with the highest power of x and the leading coefficient. So let's do some samples here. Find the horizontal asymptote of f of x, which is given right here, 2x cubed minus 4x to the fifth plus 3x plus 9, divided by 2x minus 7 plus x cubed plus x to the fifth. Now be very, very careful as we said, we're only focused on the terms in the top and bottom that have the highest power of x. Don't automatically go for the first term that's listed, because that may not be the term that has highest power. I like to pull tricks like this just to trip you up, and make sure that you are paying attention. So the term on the top with highest power of x is going to be that minus 4x to the fifth. The term on the bottom with highest power of x is going to be that x to the fifth there. So we need to compare powers of x here. Power on the top is 5. Power on the bottom is 5. Highest powers of x on the top and bottom are the same. So the horizontal asymptote is going to be the ratio of the leading coefficients, the ratio of the numbers in front of those x to the fifth terms. And that is going to be a -4 divided by a +1 or -4. So that's going to be our horizontal asymptote. Y is equal to -4. And then just one more sample here. We're going to find both vertical and horizontal asymptotes for this guy here. Now, before we go into this question here, always find horizontal asymptotes, or asymptote, I should say, because there's only going to be one. Find the horizontal asymptote first. And the reason I say find the horizontal asymptote first is because A, there is very little work that has to be done with it, but the real reason why you should do the horizontal asymptote first is because sometimes when finding vertical asymptotes, we may have to cancel out common factors, but canceling out those common factors will then impact the power of x that the bottom and or top have, and we don't want to have that potentially change what information we're given to use to find horizontal asymptotes. So horizontal asymptotes always get done first, then you go to vertical, where you may have to cancel out common factors. So horizontal asymptote first. Highest power of x on the top is 3 with the x cubed there. Highest power of x on the bottom is 2 with that x squared term there. The highest power of x on top is greater than the highest power of x on the bottom. If we go back to our 3 cases, when the highest power of x on top is greater than highest power of x on the bottom, there is no horizontal asymptote. So you could say NA, or does not exist, or DNE, or you could say none, whatever. Something to show that you know that there is no horizontal asymptote. So that's done, that's out of the way. Now the vertical asymptotes. Now we factor things out. We may have to cancel out factors. So if we factor the numerator and the denominator separately, we get x times x plus 1 times x plus 1 on the top. And for the bottom, we get x minus 7 times x plus 4. Clearly, there are no common factors here between the top and the bottom. So we just take the bottom, set it equal to 0, and solve for x. Pretty straightforward to see that our two x values are going to be -4 and 7. So these guys here are going to be our vertical asymptotes. Or VA for short. So earlier on in the video, I did mention that there is a third kind of asymptote, which I would show you. Overall, it's not focused on as much as the other two, but it is out there, and I do want to show you how to find it algebraically. This third kind of asymptote is called a slant asymptote, and it only happens when the degree of the numerator is one more than the degree of the denominator. And the way we find a slant asymptote for a rational function is with polynomial long division, or if it's possible, using synthetic. The quotient that you obtain is going to be your slant asymptote. So here I'm going to just show you one quick sample of how to find the slant asymptote. We're going to do negative 3x squared plus 2 divided by x minus 1. This is something that you can do by synthetic division, since we are dividing, my apologies, the top by x minus some number. If you do synthetic division on this, you would find that you come up with negative 3x minus 3 minus 1 over x minus 1. You can go through the whole process of taking your c value of positive 1. There's your c value. Separate out that guy, and then put the coefficients in order of descending power of x. We're going to have a negative 3, then we're going to have a 0 because there's no x term, and then we're going to have a 2. And if you go through that whole process, negative 3, and then that's going to be a negative 3 as well to give me a negative 1. There's our very quick check to see that we do indeed come up with negative 3x minus 3 minus 1 over x minus 1. The quotient portion of this, the negative 3x minus 3, is going to be your slant asymptote. The slant asymptote is always a line. So we get our slant asymptote of negative 3x minus 3. Slant asymptotes could show up in homework or a quiz. Might possibly show up in a test. Not very likely, though. There's plenty of other things that are more important for me to make sure that you know. Perhaps extra credit is where something like this would show up. But at least you've seen slant asymptotes and you know how to find them. So this wraps up our video on rational functions, their domains, properties of their graphs, namely asymptotes. In the next video or section, we are going to talk about polynomial and rational inequalities. We're going to learn how to solve these guys and how to write their solution sets. So if you have any questions or comments, be sure to reach out to me. Send me an email, send me a letter through the mail, send me a carrier pigeon with your message, whatever you have to do. Until the next video, take it easy, guys.